All right, I'll take that as my cue to get going. All right, well, good morning, everyone. Welcome to the latest installment of the Bureau of Economic Geology seminar series. This presentation is obviously via Zoom only, so quick reminders, please ensure that you have muted yourself and turned your camera off during the presentation to retain bandwidth. Questions can be dropped in the chat at any time, and we'll address Q&A at the end of the talk. So we're really very grateful and fortunate to have Prince Ochonma here with us today. Prince is a research specialist in the Department of Civil and Environmental Engineering at Cornell University. His research focuses on emissions-free hydrogen production, reactive CO2 mineralization using silicate-bearing minerals, and selective metal recovery from industrial waste streams, leveraging advanced electrochemical methods and coordination chemistry. He holds an MS and PhD in chemical engineering from the Smith School of Chemical and Biomolecular Engineering at Cornell, and a BS in chemical engineering from the University of Lagos. Outside the lab, Prince is passionate about science communication and fostering interdisciplinary collaboration to translate scientific innovation into real-world impact. So I'm excited. Should be a good talk. With that, Prince, I'll hand it over to you and take us away, please.
All right. Thank you so much, Justin, for that nice introduction. I'll just set up my slide real quick. Okay. Okay, I think I should be all set.
There you go. Perfect.
All right. Okay. Okay, thank you so much, Justin, again for that kind introduction. Hi everyone, my name is Prince. I recently obtained my PhD from the Smith School of Chemical and Biomolecular Engineering here at Cornell, and I currently work with the School of Civil and Environmental Engineering in Cornell. Today I will be discussing some of like the approach we are taking towards subsurface reactive CO2 mineralization of iron-rich minerals for simultaneous metal recovery and potential. I put the word potential there because this is still like a very open topic. Potential hydrogen stimulation. So the figure right here shown on the right essentially shows. Hold on, my pointer is not moving. I think my Zoom is frozen. Okay. Okay. Okay, we are all set. Okay.
There you go.
Sorry about that. Yeah, so the figure on the right essentially like summarizes what the topics I will be touching on today during this talk. So essentially like it would be covering three key objectives. One would be we'll discuss about reactive CO2 mineralization in calcium and magnesium bearing rock formations. Then we will take it a little bit one step further, discuss about metal partitioning in the solution phase via complexation, using selective ligands, and finally like a potential for catalyzed hydrogen stimulation in iron-rich formations. This is perhaps like one of my favorite image, and the reason is of course like it pretty much shows what where we are at currently, where we've been in the past, and where we will be in the future if we do nothing. So interestingly, you can clearly see the curve with respect to CO2 emissions keep going up by the years. Currently, if we do nothing here, we keep going, we keep emitting CO2, and probably we might hit 50 gigaton a year in the next like 10 to 20 years. That's if nothing is done. But ideally, like what I would like us to do is to focus on this black line here. And this black line simply is the right trajectory. We want to be on this black line sloping downward. And this would require net negative and net zero based technologies, and the design of materials that are like carbon free or carbon emission, low carbon emission materials. Essentially bringing to my point of CCUS, right? So everything, the design of net negative technologies or net negative material falls under the umbrella of CCUS. So CCUS simply stands for carbon capture, utilization, and storage. So essentially, you capture carbon from flue gas or from atmospheric CO2. You can either directly utilize the captured carbon to produce construction materials such as cement, or you can convert these captured carbon to fuels, etc. Alternatively, you can choose to store the carbon, the captured carbon, either from this flue gas stream or from the atmosphere in storage formations in the subsurface environment. Another interesting look at this problem would be for us to go and start looking at this problem from an emission-based standpoint. And this interesting study by Davis and co-worker published in Science in 2014 essentially like showed the distribution of our carbon emissions according to industry. And if we do take a look at the pie charts over here, we can see we do have like very high emissions with respect to electricity and short distance and residential and commercial buildings. But that's pretty in terms of like that's pretty like in on the global scale of fixing things, that's easy to fix because all we need to do is most we need to like find a way to electrify some of these industries and make the grid carbon free electricity supply from the grid. But I would like to draw attention to the bar charts on the right, which pretty much shows like, there are some industries that we will have difficult to eliminate emissions. So when they say difficult to eliminate emissions, it simply means like these are emissions that we do not have any plan for electrification, and there's no near-term plan to do away with the existing process in this industry because these are legacy-based industry like the cement industry or the iron and steel industry. And essentially, like one key conclusion from this study is the fact that to actually deal with the difficult to eliminate emission industries, we will be needing carbon-free energy carriers. So these are energy carriers that are essentially free of carbon, just like the name implies, such as hydrogen or SAFs. Essentially any hydrocarbon you can produce with very low carbon intensity. The other problem is the fact that electrification of these industries doesn't come without its own problems. So if we are going to electrify, for example, if you're going to electrify short distance transport, we need enormous amount of enormous amount of metals. So essentially, like this slide in summary, the point I'm trying to pass in this slide is yes, we need energy transition, but the energy transition also comes with its own costs. And one of the costs is, we do need enormous amount of metals, and we do need energy carriers, like for example, hydrogen, to realize our decarbonization goals. So a good approach to solving this problem would be for us to do something called like in-situ mining of metals from the subsurface environment. Um, and as a process engineer, typically like we look at big problems in form of like unique discrete unit operations. And this might be the most simplified version of the Earth you might have seen as geologists, but we'd like to look at the Earth as a huge giant reactor where we have like input streams and we can get some certain output streams. So in the input stream, in these cases, we inject some metal chelating ligand. We have catalyst that facilitates some specific reactions and dissolve CO2 in the subsurface. And the goal is to, reactively react the CO2 in these formations to partition the metal into the solution phase and allow these metals to complex with the ligand, and finally, like, catalyzed hydrogen stimulation from these ion-rich formations. But the big question is, can we really achieve this? Seems very ambitious. So can we really achieve this in a single step? So let's look at these key objectives in a discrete manner. And I would start with the first objective, which is reactive CO2 mineralization in calcium and magnesium bearing rock formations. So this is also commonly known as carbon mineralization. It is the most permanent and stable form of carbon storage. And this is pretty like an interesting concept, because it's basically converts carbon from its most stable state, which is as in carbonate form. So this is a thermodynamic downhill process, which implies that it is very spontaneous. The reactions are exothermic, and they would likely occur without the addition of like external based energy supply. Perhaps these entire carbon mineralization reaction can be represented by can be simplified to one simple equation. So you have your metal silicates. This is just a generalized form of metal silicates for this equation. And what you do need is you need some form of acid attack to break these metal silicate bonds, thus facilitating the release of metals into the solution phase. And you have these metals react with carbonate or bicarbonate ions to produce your metal carbonates in the solid phase. But this reaction also like results in the production of something we call amorphous silica. So typically you have like silica being formed in the solid phase as well. So this might look pretty simple. These reactions might look pretty simple, but it is very complex in terms of like rate limiting steps, as well as like challenges we can see just by looking at this reaction. And one of the challenge is the fact that we need protons and carbonate ions at the same time. So this would, of course, we will be requiring adequate pH control, because we do have proton generation under acidic conditions, and carbonate is typically formed at extremely alkaline conditions. So that's one of the huge exciting challenge with respect to mineralizing these silicate-bearing minerals. Perhaps the second challenge would be like the formation of the amorphous silica phase. And why this is a challenge is these silica phase tend to form passivation layers on the surface of these carbonates, mineral carbonates products, thus limiting the mineralization rate in the subsurface environment. Okay, this is frozen again. Okay. But before I will be discussing this reaction in more detail in the next coming slides, but I would like to also point out some other advantages of the carbon mineralization, including the fact that we do produce form an extremely stable carbonate products in form of like magnesium carbonate or calcium carbonate, depending on what specific rock formation is being targeted. And these materials are stable up to 400 and 750 degrees respectively. And owning from the fact that I do not think, I'm not like a geologist, but I don't think there's any any place right now in the on the subsurface environment that is up to 750 degrees Celsius. So essentially, like, we will be forming stable carbonate material in this subsurface. So we will be needing unmonitored storage, and these products are actually environmentally benign. So perhaps the most important, in my opinion, the most important reason why carbon mineralization has gained such a huge a huge attention in the past years has been the problem of the CO2 scale problem, right? So right now we are at 37.6 gigaton of CO2 being emitted on a yearly basis as at 2024. So we do have a gigaton scale CO2 problem, and typically when you have a gigaton CO2 problem, you do require a gigaton scale solution. And this solution can be in form of the vast amount of ultramafic and mafic rock present below the Earth's surface, which can act as CO2 sinks in the subsurface environment. Perhaps another interesting reason why these mafic rocks and these silicate-bearing minerals are of interest is they do have high amounts of magnesium and calcium in these naturally occurring minerals and in the industrial alkaline residue in case where you want to do ST2 mineralization. So this figure essentially shows the magnesium and calcium oxide with percent composition across various type of silicate minerals. And you can see like we have serpentine, for example, which contains like up to more than 20% of MgO SRF weight percent, going all the way to iron slag, which is a byproduct of steel making that has up to 50%, 50 weight percent of magnesium and calcium oxide SRF based weight percent calculations. So, of course, it sounds exciting. All these advantages how can we use all these advantages to our favor? Perhaps like I'm coming back to this equation I showed earlier, where we have the silicate-bearing rock needing some proton attack to break down the silicate structure, and some dissolved carbonates to facilitate the conversion of the dissolved metal into metal carbonate, silicon water. This gives an interesting pH control problem. And you can actually visualize these using the Bayesian plots, which shows the speciation of carbon, dissolved CO2 in a closed system as a function of pH. And you can clearly see that you do need an optimum of at least pH of 10 and above for you to have exclusively carbonate species, which you require to mineralize your silicate bearing rocks. So yeah, this is like an interesting problem. How can we be have an acidic and a basic based environment at the same time? Perhaps the second problem is with respect to the passivation layer problem. And I think this paper by Rim give a very good visualization of this problem. So either you are dissolving the silicate-bearing mineral using an acid-based solution, or you are trying to mineralize these rock formations. Typically, what happens is you do end up forming a very silica-rich phase, and depending on whether you're far from equilibrium or near equilibrium, the silica-coated layer this essentially controls the silica-coated layer. So the point is, ultimately, you will be forming these silica-bearing phases, and these silica-bearing phases will limit the mineralization and the effective utilization of this silicate-bearing rock. So this is a problem that we need to solve if we are going to effectively harness the power of reactive CO2 mineralization in the subsurface environment. So let's take a look at what is being done conventionally for XT2 mineralization. So one very interesting approach to bypass the pH problem is typically the external pH swing approach. So this approach essentially, like, you have your olivine rock. Of course, this is grinded to very fine particles, because these reactions were carried out above surface. So you have your olivine material, and then you subjective to some acid attack using a concentrated acid such as hydrochloric acid or sulfuric acid in this case, under mild conditions. And what happens is you end up dissolving all the metals into the solution by breaking this silica bonding structure. And you then do like a pH swing where you sequentially increase the pH of the solution to facilitate the precipitation of individual metal oxide based on the IAPs of these metals in the solution. And finally, you end up with an extremely alkaline solution. If you do start with olivine, you end up with like a pretty alkaline solution that is rich in magnesium that you can easily mineralize to produce specific type of carbonates. So this method seems pretty cool. It's it has several advantages. So you can produce hydroxides from this method, which of course, hydroxides are like more reactive phases than silicates. This method also allows for sequential removal of chemical phases that could form passivation layers during mineralization. And of course, you do have morphology and chemical specificity control, resulting in high purity metal phases. Alternatively, during my PhD, I also investigated an electrochemical approach to control the pH within an electrochemical system. So essentially, like this seems like a lot to decouple, but the key driving force with respect to this specific figure that I'm showing on the right is you do have water splitting generation when you turn on the switch. And this water splitting results in the formation of protons in the anodic chamber, and you have the formation of hydroxide in the cathodic chamber. And the protons are used to facilitate the dissolution of the silicate minerals or alkaline industrial residues. So you have partitioning of metal into the solution phase. And as a result of the pH gradient as well as concentration gradient, you can have selective transport of certain metals such as magnesium or calcium from the anode to the cathode to produce magnesium hydroxide. It's essentially like doing the chemical pH swing, which I just described, using electricity. So this is a pretty cool method if you are thinking of like above surface mineralization, but this process are not suited for subsurface mineralization because of course these reactions under the surface are very heavily kinetically limited. It takes a very long time and they are very difficult to control. So you won't be able to do these you won't be able to apply this specific approach to solving the problem of pH in the subsurface environment. But again, I'm bringing back these reactions, pretty much like my favorite reaction at this point. So this is the problem, pH control and passivation layer problem. So what have been done in the literature extensively, what people have done is the introduction of something called a buffer. So we've seen people try to use buffers like sodium bicarbonate to basically control the local pH in the solution phase, thus facilitating the production of local protons that can dissolve the silica and as well as also generating the carbonate ions due to the high pH of this solution. So using this buffer system, you can solve the pH problem by creating a local acidic pH within these very tiny surfaces. This has been done in the literature. I'm just going to show like one interesting study by my advisor actually when she was still a PhD student. And as you can see on the right, they had done an increase in the amount of bicarbonate ion in the solution, and we can clearly see that an increase in the amount of bicarbonate supply in during mineralization of serpentine, olivine rather, led to an increase in the extent of carbonation in this material. And these reactions again were done at 185 degrees, which is pretty very similar to subsurface temperatures, and pressure CO2 supply at 139 atmosphere for 3 hours. So this reaction was also done in Arizona State reaction, a very similar reaction, but the basic difference between the Arizona study and the Colombia study is in the fact that the Arizona study was done for less time, but you can clearly see that they both achieve the same conclusion, the fact that when you have sodium bicarbonate in the system, you can increase the extent of carbonation. And just to make sure that, having bicarbonate is not just it's not just supplying the necessary CO2 for mineralization, it's also acting as a buffer. They did measure the pH of these solutions, and as we can see, like there was an increase in the pH. There was a decrease in the pH with DI water, like a large delta pH compared to like when they had sodium bicarbonate in the system. So of course, like one key thing to note in this study is at some point you reach like the saturation limit where you see some asymptotic behavior. And one key conclusion was the fact that the reason why they couldn't really achieve the maximum possible extent of carbonation is as a result of the formation of these aluminum or aluminum ion and silica oxides bearing faces, which forms the passivation layer. So the key question that we started asking is, how can we engineer a process that minimizes the formation of passivation layer faces, such as ion and aluminum-based oxides and hydroxides. Um, so again, bringing back this figure just to visualize like what the objective is. So the objective is to combine both objective 1 and objective 2 in a single step. So how about we we reach the two objective in a single step? And recently, myself and a colleague of mine investigated the mineralization of ultramafic and mafic rock using this approach. So this system, essentially, we require a buffer, so we used sodium bicarbonate to control the pH. But we do introduce something different this time. We introduce a metal chelating agent. In this case, we introduce EDTA. So EDTA acts for this reaction, simply acts as a chelating agent to ensure that the metals that is being extracted during the dissolution of the silicate-bearing minerals is being chelated and kept in the solution phase. So the high stability of the complexes that is being formed during these EDTA interactions with these metals enable for fractionation of these metals and into the solution phase and prevent the reprecipitation of these metals into the solid phase, thus preventing the formation of passivation layer that could otherwise limit the mineralization. And of course, we demonstrated this for both ultramafic and mafic rock. And the reason behind trying to do this with mafic rock is a lot of times when carbon mineralization is being mentioned in the subsurface environment, people tend to prefer ultramafic rock, which is typically right because ultramafic rock has high amount of phosphoritic olivine content, which means that they are more reactive compared to the mafic component, which has very high amount of metal bearing faces, in particular aluminum and silica, which basically form this passivation layer, thus like limiting the economic possibility of harnessing mafic rock for carbon mineralization. So essentially, the highlight is based on the Bowen reaction series. We can clearly see that the distribution of magnesium and iron content across various rock types, and we can also see that these essentially also plays a role in the stability of this rock in the subsurface environment. So you have felsic, which is more stable compared to ultramafic, which is why a lot of like carbon mineralization projects typically target ultramafic rock formations. The second highlight is, we can indeed use metal chelating ligand to facilitate the selective separation of metals in the solution phase, thus enhancing carbonation. So we will be seeing how possible this is. So this is some findings from this study. This is a lot to decouple from this graph, but I think the key thing is the cycles essentially like represent the one over R CO2, which is the residual carbon mineralization capacity of the rock. And as expected, you can see like very high one over R CO2 for the ultramafic type rock types, compared to like the mafic and the felsic type of rock, which again reiterate my earlier point on why these specific rock types are of interest for carbon mineralization. But the other thing we need to see is the bars. The bars essentially should correlate like the carbon mineralization extent. And as we can see, we do have very high carbon mineralization extent with ultramafic rocks compared to mafic rocks. But we do believe like, achieving 20 greater than 20% mineralization extent with mafic rocks such as olivine gabbro, and achieving very good up to 10% of mineralization with picrite results is actually a very huge accomplishment, because typically these materials are like very unreactive, and they do not you would rarely find studies that have shown that these rock can reach these high carbon mineralization extents. And we do believe the reason why these extents were able to be reached is because of the partitioning of specific phases. In particular, if you do look at the aluminum, the amount of aluminum in the solution phase, you can clearly see high amounts of aluminum remaining in the solution phase. And mind you, these reactions are actually like performed at very high pH. So every single one of these reactions are typically above pH of 9, which is very favorable for the formation of aluminum hydroxide, which typically forms those passivation layers you see in when you try to mineralize mafic rocks. But we were able to show that you can indeed partition this aluminum into the solution phase with the addition of an organic ligand such as EDTA. So of course, the highlight is the presence of metal chelating solvents such as EDTA. We do report that to enhance metal dissolution in the solution phase, and we believe that is very key in the enhanced carbon mineralization extent that we obtained for this study compared to existing literature. So the key question we typically get is, okay, so how do you really select the solvent? I mean, there are several selection criteria, including the number of the density of the solvent, which essentially shows like how many active sites the solvent have. But of more interest from a commercial standpoint, I do believe like one very key parameter that influences solvent selection is the regenerability of the solvent. So in order for you to figure out like if this solvent can be regenerable or not, we need to take some cue from downstream processing. So typically during downstream processing is done using a process called electrowinning, where your metals are dissolved in typically an inorganic based medley, and we do something, and then they are reduced on an electrode surface to produce like high purity metals. So what we did study in this study was we tried to see how does the presence of this nickel, so we use nickel in this study, so how does this nickel base complex, um, how what is the ease of regenerating the solvent after you've used the solvent for metal chelation? And essentially, the question that we were asking when we designed the study is, can we engineer an approach for coupled electrochemical metal recovery and solvent regeneration via electrowinning? Just to provide an important like explanation of what is being done. So typically, like in the industry, they use a one-chamber cell where you have like your cathode and your anode. On the cathode, you have your reduction of your metal to produce your solid base high purity metal phase. And on the cathode, we have something called the OER reaction, which is the oxygen evolution reaction that produces proton. But in this study, we decided to use a two-chamber cell because we wanted to prevent the formation of hypochlorites, which typically like poisons the ligand and results in the degradation of these ligands, which is why we do not, these ligand-based systems are not typically used directly in the industry. So that's why we have these two electrodes, this two-chamber cell. So we have an anion exchange membrane in between to facilitate the transport of the chloride ion that is dissolved in the solution. So the chlorine is actually coming from the nickel-based chloride precursor that we use for this experiment. We did use titanium sheet electrodes for the cathode for this experiment because titanium sheet is industrially scalable and pretty cheap, and we use platinum sheets for the anode because platinum is a very strong a strong electrode for the OER reactions. So this reaction we carried out with and without CO2. So this I wouldn't be talking about the CO2 reactions for now, but the key thing to note is there's typically a reported competing reaction to nickel-based complex reduction called the HER reaction, which consumes the electrons that should be typically consumed by nickel reduction to produce hydroxide and hydrogen. Right. So we do want to prevent these reactions from happening in these systems. So we will be investigating different types of solvents, including sodium hydroxide, MEA, and DTA. So we did select this solvent for several reasons. MEA is a very common CO2-based solvent that is used industrially. And it also has a very good stability constant with respect to nickel. DTA has perhaps one of the strongest stability constant with respect to nickel. But the key question we want to ask is, what would be the trade-off between chelating strength of these solvents during metal recovery and coupled metal recovery and carbon mineralization and the regeneration of the solvent? So how much, what strength of solvent would be necessary to achieve both results? So that's why we selected an extremely high chelating solvent such as DTA in this case, and a very mildly complexing agent such as ammonium hydroxide and MEA. Perhaps like you might be wondering why, why should we worry about regeneration of the solvents? And the most important thing to note is, this is essentially like if it's cost driven. So these solvents are like very expensive. So it means that, if you have to use them once, you would need like a large amount, and that's going to affect the operating cost of your whatever commercialization you're trying to use this to do. So yeah, so the cost is very important, and so that's why you need to be able to design your solvent in such a way that you have very high regenerability and very good chelating strength at the same time. So let's take a look at some of the results of these carefully designed study. So the first thing to note is we do have, we perform something called the linear sweep voltammetry. So this is an electrochemical technique that measures the current response at an electrode while applying a linear charging, changing potential between the working electrode and the reference electrode. So the insight we typically get from LSV is, one, we get like the onset potential, which is very important for designing the potential window for that you want specific reactions to occur. And so we can infer based on the slope of the plot right here, like this, the varying slope could be indicative of like easy transition from one regime to another. So as we can see from this plot, you see we do see lower onset potentials with respect to ammonium hydroxide compared to DTA. Of course, this is because ammonium hydroxide binds more loosely to nickel compared to DTA, which binds very strongly to nickel, thus preventing, you need more energy to be able to extract nickel from DTA compared to ammonium hydroxide. And also you can see the changing slope indicative of the fact that, with ammonium hydroxide, the transition from one regime to the other is it's shorter than with respect to DTA. So we will expect to like rapidly produce more hydrogen via the hydrogen evolution reaction with the solution bearing DTA compared to that with ammonium hydroxide. And here's like the quantitative results just to basically interpret what the LSVs has already told us. And as you can clearly see, the black bar chart shows the nickel yield rates, which is represented as milligram per hour per area of the electrode surface. And you see, we do see like high amounts of very overlapping amount of nickel yield rates with respect to ammonium hydroxide and MEA, but we do see significantly low amounts of nickel production using DTA, which is indicative of the fact that you do need more energy to extract this nickel when you use DTA as the CO2 capture solvent for nickel extraction from these olivine rock materials. And of course, the Coulombic efficiencies typically measures like how much efficient you are with respect to the energy. And we can clearly see that, there's a decrease in the Coulombic efficiency with DTA compared to ammonium hydroxide and MEA. So Ni-DTA binding might just be too strong for electrodeposition, which is resulting in very low Coulombic efficiencies. So to be able to really figure out what's really going on, we did like a time-based study, just for a much more longer time scale to figure out like if what is really happening with like respect to each individual solutions. And the two key things to note here is when you look at the ammonium hydroxide and the MEA, you can clearly see like high amounts of nickel recovery efficiencies as we go for time. And of course, you do see an asymptote, which is expected since the concentration of nickel in the original solution tend to decrease over time. So you need more and more and more energy to extract all the nickel from the solution. However, like uniquely, what I would like to point our attention to is like the anomalous behavior with respect to DTA. We do see a rapid increase, and then all of a sudden, after 1 hour, we do see like some kind of like asymptotic behavior with EDTA. So this is an early asymptotic behavior that's not expected, and we started hypothesizing what could be the reason why we are seeing this early asymptotic behavior. And what we did notice was this could be as a function of pH increase. And I'll tell you, going back to our reaction scheme, if you do remember, I did say we do have a repeating HER reaction, which produces hydrogen and hydroxyl ions, thus making the catholyte mixture extremely alkaline with time. But how does this really affect EDTA, nickel EDTA stability? Of course, we have to go back to thermodynamics. And if you do see the speciation curve of NIDTA as a function of pH, we do see like at high pH, we do have nickel preferentially forms as NIDTA2, which is the green plot here, compared to like lower pH where you have nickel would preferentially exist as either nickel 2 plus, and at mild pH conditions, nickel would exist as NIDTA only. And why is this important? If you do take a look at the log K values for NIDTA and NIDTA2, you can clearly see the higher stability with NIDTA2 compared to NIDTA, which implies that to be able to control these extraction, we might need some sort of pH control in these systems, and we did achieve that with the introduction of CO2. So in this system, we introduce CO2 to act as a buffer to control the pH of the solution during electrowinning. And as we can see, like these dots represent the delta pH of the solution. That's the difference between the pH before and after. And as we can clearly see, like the delta pH with CO2 compared to the delta pH without the CO2 is clearly lower, which makes sense because we do have like CO2 reacting with the excess hydroxy ion to produce bicarbonate ions. And how does this affect the system? We do see an increase in the amount of the nickel recovery efficiency with respect to DTA. We do see tiny increase with respect to ammonium hydroxide and MEA as well. And what we do believe is at this point, we start forming nickel DTA, and we start forming a mixture of nickel DTA and nickel DTA2 in the system. And since nickel DTA is more easy to win out of the for nickel extraction, we do see slight enhancements in nickel extraction. So in summary, like CO2 in this system could act as a buffer and replace nickel in active binding sets or facilitating nickel deposition. And I think the most important conclusion for this is when you design solvent-based systems for integrated mineralization and metal recovery, the regeneration potential should be a key criterion in the selection process. Okay, so I think so this brings us back to this figure. So we have discussed on reactive CO2 mineralization in calcium and magnesium rock formations. We've taken it a step further to show that we can do both CO2 mineralization as well as metal partitioning to the solution phase with the introduction of a ligand-based system that act as both a CO2 carrier as well as a chelating agent for the systems. So the key question going forward is, would it be possible to achieve all three objectives in a single step? That's like a key question. I personally hope to keep investigating in the next near term. But let's take a look at what really happens, or like what people know about hydrogen stimulation in phalitic formation. So currently there are a lot of like reaction and pathways that have been popping out lately. But like the currently accepted reaction pathways, the one of serpentinization, such that you have ion being oxidized from ion 2 to ion 3, resulting in the reduction of water and the production of hydrogen as a result. So this reaction perhaps is the basic reaction for hydrogen stimulation in these subsurface environment. And interestingly, like there's like an interesting study by Levy and co-workers where they had a wide range of they plotted hydrogen generation as a function of different parameters, including the temperature at which these reactions occur, the time scales at which this reaction occur, and also like the different rock mineralogy that people have hypothesized could be responsible for hydrogen generation in the subsurface environment. And I want to point out that like this study are nowhere near like the reality in terms of like the size of particles used for this study. Typically the studies are done in a reactor system above surface using very fine particles. But at least we can gain some insight into what is really going on. One key thing to note is, of course, you can clearly see an increase in the generation potential of hydrogen with respect to temperatures, and it pretty much like evens out after 200 degrees Celsius, which means that like increasing the temperature further might not necessarily like be might not necessarily like lead to more hydrogen generation. I think another key thing to note is you can clearly see this isolated dot here, which is magnetite at low temperatures. You see very high hydrogen generation potential, which is indicative of the type of rocks that you might be interested in if you are trying to stimulate hydrogen in the subsurface environment. So um, this is like a study that like it's currently ongoing, and we are excited to see where this would lead. But my proposition would be, how instead of just like independently stimulating hydrogen, if we could combine all three key objectives, it sounds pretty ambitious, but that would be like a pretty cool way to store CO2, produce metal, and also produce hydrogen alongside. And some of these interesting studies have provided insights on the type of rock mineralogy we should be interested in looking for, and the type of temperatures at which we might be needing to perform these reactions, which are very, very similar to temperatures at which we do reactive CO2 mineralization of silicate-bearing minerals, and are also favorable for metal partitioning into the solution phase using ligand-based system. So of course, like this is pretty interesting because you do have some technological edge with respect to leveraging natural heats and existing pressure gradients within the subsurface environment to drive this reaction kinetics and enable stimulated hydrogen accumulation without the need for compression. Of course, essentially, like what this bullet point is saying is that you do not require significant energy requirements compared to green hydrogen and steam methane reforming, which implies that on a cost-based level, if you do to get the T, I've seen some a lot of like TEA lately on this system have been projecting the $1 per kilogram of hydrogen it's possible if you either stimulate this hydrogen or you naturally search for this hydrogen. And interestingly, also, you can potentially lower the carbon footprint significantly with CCS compared to blue or green hydrogen. So basically, in conclusion, you can have local pH control. It's actually very critical for facilitating or enhancing the solution and mineralization of alkaline species in rock formations. Organic ligands such as EDTA can facilitate the solvation of metals while enabling mineralization of calcium and magnesium in ultramafic and mafic rocks. The selection of ligand is very important, and careful consideration should be made with respect to chelating versus regeneration, because extremely strong complexing agents could lead to like lower deposition rates during downstream processing, and could lead to like higher cost of processing your metal soup. And also like there exists like a huge possibility for combining hydrogen stimulation in this phylitic formation, which typically have very slow mineralization rates. So my next steps would, I'm currently excited about unraveling the possibility of like combining all three objectives in a single step. Um, of course, like I would like to acknowledge, the various funding sources that have made the research possible, and the project possible, including APA-E, as well as the Department of Energy and the Link Energy for funding my PhD. And I would like to acknowledge my PI, my PhD PI, Grishma Dakota, as well as all members of her group. I'd like to acknowledge my colleague, Shreya Katre, who's currently a postdoc in Finland, who worked extensively, who I worked with extensively on reactive CO2 mineralization and metal recovery. And finally, my colleagues, Tianhe and Akansha, who worked on the e-metal separation project with me, and my undergrad mentee, who's currently a PhD student at SUNY, who also work with me on this project. So thank you for your time and attention. And if you would like to read more about some of these findings, I have the QR codes of these papers. You can, if you want to read about the ultramafic rock mineralization and metal recovery, you can scan the first QR code. Otherwise, you can scan the second QR code for the mafic rock mineralization and metal recovery. And if you are interested in the electrochemical dissolution of silicate residue study, you can scan the third QR code. Thank you guys so much.
All right, thank you, Prince. Quite a talk, lots of information in there. We've got just a couple of minutes here for Q&A. Sue, I saw you drop a question in the chat earlier on. Would you like to turn on your camera and ask your question, or would you like me to do it? You've got it.
You,
Perfect.
you can do it, and I
Yeah,
okay.
the question that Sue posed is, I hear two statements made about mineralizing, but they are rarely defended. One, carbonate being solid rock, quote unquote, is permanent. However, carbonate is quite soluble in water, especially in the presence of CO2. Reactions that are shown to the right can also go to the left. Second question or statement that's not defended, carbonates are harmless, but the dissolved gas and mineral will release other major and minor ions. What are these? Where will they go? Are they harmless?
That's a pretty very good question. To answer that, I think the first one was essentially like I think it was on these, yeah, right. So when I say carbonates are stable, so what I do mean is they are thermally stable, subsurface environment up to like temperatures of as high as 400 to 750 degrees. Of course, you know, when you have dissolved CO2 and under certain alkaline conditions, you could have your carbonate like redissolve and you have like the backward reaction occurring over time. So yes, that's a possibility. But ultimately, like you end up releasing trapped CO2, which of course I mean, there's like I've been following CapFix for quite a while, and I don't think there've been any reports of CO2 seepage back into the environment. And they've been sequestering CO2 using these methods for quite a while now. But yeah, indeed, I do agree that it's possible for the backward reaction to happen under certain conditions, especially when you have like acidic base conditions. You can have the pretty much like you can have like the formation of carbonic acid, which is very unstable, could lead to the formation of CO2 gas and water. So the second question is, you do have the formation of like silica. Yes, indeed. Um, that is the exact reason why the use of complexing ligands is, and that's the entire focal point, or would I say the value proposition of this talk is the use of selective ligand to prevent the reprecipitation of these metals. So silica essentially is very soluble under alkaline condition. So if you can keep your mineralization solution extremely alkaline, your silica would most likely stay in the solution phase. So typically, like silica, amorphous silica form under extreme acidic conditions, or where you have, or when you under like conditions where you are below the solubility of this material. So I would say like the entire point of like pumping in solutions and removing these solutions can prevent the formation and reprecipitation of amorphous silica over time, thus like basically enhancing the purity of the products that you are getting. So rather than getting a mixture of glass and carbonates, you know, you do have your carbonate and your silica in the dissolved form, which you can extract back to above surface alongside the metals that are being trapped in these ligand-based systems. I don't know if that does that answer your question?
Well, I wasn't worried about the silica making glass, but
Mm.
about your mafics are often, the desirable, if it's basalt, it often has very soluble constituents in it because that makes the reaction go. So I was talking about that glass, and that glass could have a lot of things in it. So the reaction product, the carbonates, are well understood, and they may scavenge a lot of the. I've heard it said that the carbonates will scavenge the metals that are in the system that are released by the dissolution process. But I've seen very little solid work on it, so I'm still looking for people who are watching, for unexpected, environmentally difficult reactions, that things that are liberated, that are problematic. So you dissolve rock and you get a solution, and if the precipitates are benign, but is the solution benign? I don't think you could also use the Iceland experiments because they wouldn't know if there were CO2 being released. It's a volcanic area. There's a lot of CO2 being released. So there's a lot of high flux. See, it's very difficult to. So people often say this is the best method because of its permanence, but I don't feel like I feel like there's loose ends to that statement that are not very well researched. So I wondered if they were of interest to you.
Yeah, so yeah, that's very correct. Like so like of course every um potential solution have like some loopholes, and that's the entire point of our existence, right? Trying to find out we keep finding ways to solve these loopholes. Like another problem comes, we try to solve it. So but I do think though, like the essential point of like this is still like a very early research. So like a lot of the solvents that have been designed have not been selective. So it would be like pretty interesting to know what specific constituents you're referring to, or like if we can see these constituents that are not benign. Maybe we can design some ligand-based systems that would like specifically attack these constituents. So the entire point is ultimately this why this is different from the cap fix or the Iceland-based idea is that ultimately we will be pulling out the solution back above surface. So everything comes in the fluid phase comes back out. So there's no like possibility for long-term interaction between the carbonate and probably some dissolved species that are not environmentally benign. So everything it's basically an input-output based system where we inject these ligand solution with dissolved CO2, mineralize the CO2 and pull out back the fluid phase that we believe should be rich in certain minerals, and possibly some of those constituents you're referring to will also be pulled back out for further processing. So that's basically the concept. So I think that's how this differs from the cap fix based currently ongoing mineralization approach.
Thank you.
All right. Well, we're about 5 after here, and so unless anybody else has a truly burning, fiery question, I'd say we'll go ahead and leave it there for now. All right. Well, hearing none, thank you so much, Prince, for the really interesting talk. We really appreciate it and enjoyed it. And thanks everyone for coming.
Hosting for hosting.